Welcome. This is a, a quick video on how to graph complex numbers and the modulus. This first question says here, write the following complex numbers in rectangular form and graph in the complex plane. Label the points A, B, and C. So first off, this first one, your real part goes first, and then it looks just like a regular ordered pair of X and Y. So your real part, -6, and then comma, your imaginary part, -4i, so you would just write -4. And so the next one would be 5, comma, and then -i would be the same as -1. And then C, -4 plus 6i would be -4, comma 6. Pretty straightforward. On the complex number plane, the real plane is horizontal, and the imaginary plane is the vertical axis. And so -6, comma -4, you go over here to -6, and you go down here to -4, and that point right there would be the point A. B, 5, -1, so over here to 5, go down -1, that would be the point, the B. That's the complex number B, which is 5 minus I. And then -4, 6, that'd be -4 up 6. So this point right here is C, and that's what this looks like. All right. On this next one, write the following complex numbers and in rectangular form and graph them in the complex plane. Label the points D, E, and F. This was just a little bit different. D, 3i minus 5. If we're putting this in standard form for complex numbers, that's A plus BI. And so 3i minus 5 is the same as -5 plus 3i. And so in rectangular form, that becomes then -5, comma 3. E, -3i, written in that same form, A plus BI, it just means that there's 0 real parts. All we have is the -3 that in the imaginary part. So that's the same as 0 minus 3i. And that over here would be 0, comma -3. And then finally F, 4, it has a real part, but it doesn't have any imaginary part. So it's 4 plus 0i. And so its rectangular form would be 4, comma 0. So if I'm going to graph these, is just like here, this last one. I go -5 in the real part and 3 for the imaginary part. So that's right there. That's point D. And then E, 0, -3, 0 for real, but the imaginary is down here at -3. And so this point right here would be E. And then for F, the 4, comma 0, purely real, no imaginary. There's 4 for the real and 0 for I, and so this is F. And that's how that works. So on this one, it asks us, find the moduli of the following complex numbers, exact and rounded to 2 decimal places. So 4 plus 7i, if I were to graph this out, on the real part, here's the real axis, and here's the imaginary axis. So I go over here, let's call this 4, and then 7 would be up here. And so this point up here, 4, comma 7, what we're looking for is this. And if you kind of build a little right triangle, it's basically just the Pythagorean theorem. So this is 4 and this is 7. And so we would write that this modulus, which we often refer to as z, the absolute value here, z, is the modulus, is the same as the square root of 4 squared plus 7 squared. And 4 squared is 16, plus 7 squared, which is 49. If you take 16 and add it to 49, you'd get 65, I want to say. And that's the exact value, the square root of 65. If we could simplify that, we would, but if you take 65 and break it into its prime factors, it comes down to 5 times 13. And so there is only one 5 and there's only one 13, so it cannot simplify it as a radical any more than that. But in terms of its rounded to the hundredths place, here I would open up my calculator and I would say, the square root of 16 plus 49, and that's 8.6. Just to check here, the square root of 65 is what I was thinking here, and that's, again, it's that same decimal. So 8.06. So rounded to the hundredths place, that's 8.06. And both of those answers then are required for this. So remember, how do I simplify radicals? And then what does that look like when we're rounding them to the hundredths place? All right. For this next one, so this is number 1. For number 2, if I was over here 1, 2, 3, and then down here 1, 2, 3, 4. This is 3 here, this is minus 4. And I put this in my calculator here of 3 squared plus negative 4 squared. This looks like a 3, 4, 5 triangle. But yeah, if you're not sure, it's always fine to go ahead and plug it in. 3 squared, that's, parentheses are not really necessary, but if you get in the habit of using them, then you're not going to make the mistake like you make sometimes when you forget to put it in for the negative numbers. So I've got negative 4 quantity squared here, and that gives me 5, just like I thought. So this is equal to 5. Its exact value is 5, and rounded to the hundredths place, it's still 5. So those are our answers there. Find the moduli of the following complex numbers, exact and rounded to 2 decimal places. So 10i. Now, think about what that means. In standard form, that's 0 plus 10i. If I were to graph this, it would just be right down here. Bump, 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 bump. 10i. This is my imaginary. Here's my real. And it's just that point that's 10 down. There's no triangle to be made of this. And so its modulus, I'm sorry, it's not down, excuse me. It would actually be up here, 10. And so this is imaginary. There's no real component to it, and so it would just be up. And so its exact value would be 10. And its rounded value would be 10. And so that's what you'd get for number 1. Number 2, 12 minus 7i. So I go back over here, and I just want to think here. Here's 12. Here's down 7. So 12 in the real, 7 for the imaginary. And I want to find that distance there. And so this is minus 7, and this is 12. And if I take the square root of 12 squared, and I add it to negative 7 squared, and I put that in my calculator, 12, and we'll go back and put it in parentheses, 12 squared plus negative 7 squared, and that comes out to approximately 13.89. So over here, that's 13.89. But exact, for that, I want to just take What's 12 squared plus negative 7 squared? That's 193. And so what I've got is the square root of 193. And my question then is, can I simplify 193 as a radical, the square root of 193? So I know that prime numbers, it's not divisible by 2. For the 3's, I can add the digits. 1 plus 9 is 10, plus 3 is 13. 13's not divisible by 3, so neither is 193. 5 only if it ends in 0 or 5. Let's see, 7. I don't think it's divisible by 7, but you can always just check. 193 divided by 7. Nope. Get a decimal. Let me see. The next one is 11. Pretty sure it's not divisible by 11. Once again, 193 divided by 11. Get a decimal. 13, maybe. 193 divisible by 13. Nope. The next prime number after 13 would be 17. So if I say 193 divided by 17. Nope. And when you get to 17, 17 squared is 289. So we've gone far enough. That's none of those prime numbers are divisible into 193, which means probably that 193 itself is actually prime. So we would just leave this as our answer. And so these are our answers. Exact, rounded is the same value. Square root of 193 rounds to approximately 13.89. And so that's where we're at. Keep studying hard. You got this.